The change of force principle is another aspect of the first law of motion. So let's take a look at how this works by examining the situation of a billiard ball rolling into the cushion at the side of a table. Let's start by focusing on the interval between events 1 and 2. So here the ball is rolling towards the cushion, but is not yet in contact with it. The first thing that we need to figure out is the interaction diagram. Our system is the ball, and we ask ourselves the key question during this interval: what objects are interacting with the ball? So the ball is in contact with the table, and we get the earth for free. What type of interactions are these? With the table, we have a normal interaction, and with the earth, we have a gravitational interaction. The next thing we'll think about is the horizontal state of force. So in this situation, with our two interactions, these are going to produce forces in the vertical direction only. We were told that the friction interaction between the ball and the table is small enough that we can ignore. That's why we didn't include it here. So there's no horizontal forces at all, and in that situation, we simply call the state of force balanced. If the state of force is balanced, then the state of motion in the horizontal direction will be constant velocity or rest. We know the ball is moving, so we'll choose constant velocity. Now we're ready to draw a force diagram. As always, our system object, the ball, we represent as a point. We have two interactions, and these will produce vertical forces. In the vertical direction, the state of motion is rest, so the vertical forces must be balanced. So we've drawn force vectors of equal length. We've included the ticks to show that those forces are the same length. And we have our complete force diagram. Let's think again about the movement in the horizontal direction. Is it speeding up or slowing down? Well, we decided it was constant velocity, so there is no change to its velocity. And drawing the velocity graph, if it's moving at a constant velocity in the positive direction, then we'll draw a horizontal line. Now, to see the force change principle in action, we need to have a change in the interactions. So at event 2, the ball begins to contact the cushion at the side of the table. So during this interval from 2 to 3, there's a new interaction. So let's draw an updated interaction diagram. The ball is still the system. It's interacting with the table and the earth just like before. And now we have a new interaction with the cushion. This is also a contact interaction, so it gets the label N. In the horizontal direction, the state of force is now going to be unbalanced. There's going to be one horizontal force. Because the forces are unbalanced in the horizontal direction, the velocity is going to change. So the state of motion is going to be acceleration. When we draw our force diagram, we want to be careful because some parts of it should look identical to the previous force diagram. So we do this as carefully as we can. These forces are the same as before. Now we have a new force. The cushion is exerting a force on the ball, and it's going to exert that force in the negative direction. We now have two normal forces in one force diagram. This could become confusing. So the advice in this situation is to provide additional labels. So we'll have the normal force of the table on the ball. We'll show that with this notation T-B. And we have the normal force with the cushion on the ball, C-B. So now these are distinct. We know that the state of force is unbalanced, and so that means we need to draw our wiggly acceleration vector. And now let's think about its motion in the horizontal direction. Is it speeding up or slowing down? So it's moving in the positive direction, but its acceleration is in the negative direction. And that's our recipe for slowing down. So during this interval of time, its velocity is going to change from this large positive velocity to a velocity of 0. That's when it will finish slowing down. And here is where we see the force change principle. At this event, event 2, the interactions change. The new interaction from the cushion causes a new force, and that changes the state of force in the horizontal direction. So at that moment, its velocity begins to change. So as soon as the forces change, as soon as the interactions change, the velocity begins to change. But we have to remember, it's not a sudden change. It doesn't immediately drop to 0. It takes time for a velocity to change. And that's a really important piece of our understanding. Velocities never suddenly change in a realistic situation. They always take time to change. We can clearly see the change between the state of motion, constant velocity, and constant acceleration here, right at event 2, which occurs right when the forces change. And that's what our force change principle is all about. Okay, there's no delay. As soon as the forces change, the state of motion changes. But it takes time for the velocity to change.